Okay, good morning. We are going to continue what we started last day with the simplex method. So I'm going to do a more complicated problem today, more variables. So something that cannot be drawn on a graph, okay, because it's three-dimensional and we could actually have more variables. I would do more variables, I just lack the space. If we were on campus where I have 50 feet of board, a little different story. And we're also going to look at an alternate type of problem to the simplex method. So I'm going to grab a problem from my book, okay? And so what we're going to do, hold on a second. Okay, we are going to, oops, don't fall. Here's the problem. We are going to maximize, and usually I like to think of this as profit. Think of this as a money kind of situation. We're going to maximize 2x1 plus x2 plus 3x3, the sum, okay? Subject to, we write like this, subject to x1, x2, x3, all being greater than or equal to 0. So we're looking at non-negative values. In real terms, x1, x2, and x3 would be my constraints, my resources, might be time, might be money, might be manpower, whatever. So it's not reasonable that those could be negative values if that's the situation. And then the inequalities we're going to solve is x1 plus x2 plus x3 is less than or equal to 59. Two x1 plus, sorry, it's hard for me to see this, 3x3 is less than or equal to 75. And finally, x2 plus 6x3 is less than or equal to 54. If you actually have the section brought up on your screen or in your computer, it's actually problem 18, okay, section 9.3. I'm just grabbing that one because it's a nice beefy, let me make sure I wrote it down correctly. Yep, okay, I wrote it correctly. All right, so the first thing we do is we create a system of equations by introducing what are called slack variables. That's what we looked at last day. Right now, these are inequalities. x1 plus x2 plus x3 could equal 59, or it could be less than 59. Okay, so if I introduce another variable to fill the void, take up the slack, in other words, then I can say it's equal. So we're going to introduce slack variables, and we're going to write the following. So we have x1, actually I'll do this in a different color. x1 plus x2 plus x3 plus slack variable 1 equals 59. 2x1 plus 3x3 plus slack variable number 2 equals 75. x2 plus 6x3 plus slack variable number 3 equals 54. And I rewrite this by throwing everything on the same side. So negative 2x1, negative x2, negative 3x3 plus p equals 0. Now from this, okay, from this situation here, I can now create a matrix and go through the matrix process, okay? But the key is it's not the usual goal. I'm not looking for the lower triangle of zeros. I'm not trying to get this in Jordan canonical form. I'm not even trying to get it in row echelon form. I'm trying to create unit columns for particular places on the system here. So when I write this as a matrix, we'll have 1, 1, 1, 1, 0, 0, 59. Okay, then 2, 0, 3, 0, 1, 0, 75. Then here, 0, 1, 6, 0, 0, 1, 54. And then the last row, negative 2, negative 1, negative 3, 0, 0, 0, 0. Okay, now in the notes on Canvas, you'll see simplex method. So I've got a simplex problem that I've worked out in detail, similar to what we're doing on this one. So just kind of give you extra explanation. So again, this is the X1s, this is the X2s, the X3s, slack variable 1, slack variable 2, slack variable 3, and then the constants. Right now, if we stopped right now, X1, X2, and X3 would all be 0 because these are not unit columns. And if X1, X2, and X3 are 0, then P would be 0. P lives right there. So that is a viable solution, although it's not a very interesting problem. So again, the X1 column, X2, X3, and so on. So I have to choose my pivot. So I showed last day, I start with the largest negative number on the bottom row, which in this case is -3. And now I look at the ratios of these terms, and I want the smallest positive ratio. I have 59 over 1. I have 75 over 3. I have 54 over 6. 54 over 6 is the smallest value. So that's going to become our pivot. Okay, that one right there. So I'm going to do this. So I'm going to multiply that row by 1/6. Now I'm going to have to write a little bit smaller. I got to get everything on here. So 1, 1, 1, 1, 0, 0, 59, 2, 0, 3, 0, 1, 0, 75. Now I'm multiplying that row by 1/6. Okay, yeah, I have a little bit tighter. I'll put 1/6 row 3, so we know what's going on here. So 0, 1/6, 1, 0, 0, 1/6, 9, and then the bottom row, -2, -1, -3, 0, 0, 0, 0. Okay. So we are going to create a unit column. A unit column, think of it like a unit vector. Okay. A unit vector is a vector of length 1, but a unit vector that has a 1 and all the rest zeros is often a preferable form. So I'm going to take negative row 3 and add it to row 1. Okay, let me rewrite row 3 first. So negative row 3 plus row 1, so 1, 5, 6, 0, 1, 0, negative 1/6, and negative row 3 plus row 1, that would make that 50. Okay. Let's take negative 3 row 3s and add it to row 2. So that would be a 2. Negative 3 of these, that'd be negative 3/6, if you will. Okay, and so that'd be, I'm going to write it as negative 3/6, so they all have the same denominator. 0, 0, 1, negative 3 of these. Okay, and negative 3 of these, that'd be negative 27 plus 75. That would be 48. Okay, so quick check here that everything works so far. So I have a negative, boom, 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 and a negative 3 of those. And then finally, going the other way, I'd want 3 row 3s plus row 4 to put my 0 there. So that's going to be negative 2. 3 of these plus this, that's going to be negative 1/2. 3 of these plus this, that's 0, 0, 0. And I can go ahead and write 1/2 on that bottom row. And 3 of these, that'd be a 27. Now, if we stop now, we have a viable solution. So again, I want to walk you through this. You're not stopping now, but after each round, we can check and see, does our answer make sense? Right now, we'd still have the X1 and X2 being 0, but right now, X3 would be 9 and P would be 27. So let's check that out. 0, 0, and if that was 9, this would in fact be 27. But then when I go to my inequalities, if X3 is 9, actually, let's go here. If X3 is 9 and X1 and X2 are 0, that means I have 50 unused units. Okay, and that's what that says right there. That's S1, 50 unused units. Here, okay, if X3 is 9, that's 3 times 9 is 27. X1 was 0, so now I have, looks like 48 unused units of S2, and that's what that says right there. And then the third equation, if X3 is 9 and X2 is 0, then I have 6 times 9 is 54. I used up all of S3, and that's S3, which would be 0. So you see that matches my system at this point. So let's go for the next round. So the next round, -2, -1/2, we go here. I have 50 over 1. I have 48 over 2. 9 over 0 is not a positive value, so that's not one that I'm going to consider. So it's 50 over 1 versus 48 over 2. 48 over 2 is smaller. So that will become my pivot. So 1, 5, 6, 0, 1, 0, -1/6, 50. I'm going to multiply this row by 1/2. So that would be 1, -1/4, 0, 0, 1/2, -1/4, 24. And then everything else stays intact. Okay, so at this point, now what we'd like to do is do the row operation. Eventually, we want that guy to be 0. So I go up first. I'm going to take negative row 2 and I'm going to add it to row 1. So I'm going to rewrite row 2. This is a little small. Hopefully everybody can read this correctly. So negative row 2 plus row 1. That's a 0. Negative row 2 plus row 1. Now, I can do this in my head. I can do this in my head rather easily without even thinking about it. But I think it's dangerous in general to take multiples of fractions of different denominators and add them together. So I'm going to suggest maybe use your calculator. You're going to take negative of this plus this. So I'm going to have 1/4, and I'm going to add it to 5/6. And that gives me 13/12. Okay. 0, 1. The negative of this, that'd be -1/2. Now I have the negative of -1/4 added to 1/6. Or excuse me, added to -1/6. So that's basically 1/4 minus 1/6, which of course would be 1/12. And then the negative of this added to this would be 26. Okay, I don't need to do anything to row 3. It's already good. Already got a 0 there. And I'm going to take 2 row 2s and I'm going to add it to row 3. So 0, 2 of these, that would be -1/2 plus -1/2, that'd be -1. 0, 0, 1. 2 of these, that would be -1/2 plus that half, that would be 0. 2 of these, that'd be 48 plus 27, that would be 75. Now, again, we have a viable solution at this point. So I'm going to examine what that would be. Right now, X1 and X3 are unit columns. So X1 would be 24, X3 would be 9. If X1 was 24 and X3 was 9, 2 times 24 plus 3 times 9 is in fact 75. That's good. If X1 was 24 and X3, again, I'm reading them from here, was 9, 24 plus 9 is 33. That would leave 26 unused units. This is S1, and notice 26. Hey, if X1 is 24 and X3 is 9, then I have 48 plus 27 is 75. I would have used up all of S2. That says S2 is 0 because that's not a unit column. X2 is 0, X3 is 9. There's 54. I used up all of S3. And once again, so if I read my solution from here, you notice it satisfies all of the equations and inequalities, but it is still not our final answer because I still have a negative in the bottom row, okay? So since I have a negative in the bottom row, I've got 26 over 12/13, let's see, that would be 24. That's negative. I don't consider it. I have 9 over 1/6. That's 54. That's way too big. So there's my pivot. Okay. And by the way, that's a good thing because it means eventually this is going to become a unit column. I'm not backtracking and doing any other columns. So I am going to multiply this row by 12 over 13. So 0, 1, 0, 12 over 13. When I multiply this by 12 over 13, what will that give me? Negative 6/13. If I did that correctly. Did I do that correctly? Let's see. I'm multiplying by 12 over 13. Yes, 12 over 13. That would give me 1/13. 12 over 13, that'd give me 24. Now I'll repeat everything else. If all goes well, this should be the next thing I do should be the last step of the problem. We'll barely fit everything on here. Okay, it's gonna be a little bit tight, but we'll make it work. All right, so my pivot, and I like to circle these so I can always see them. I want to make this into a unit column, so we'll go slow. So 0, 1, 0, 12/13, negative 6/13, 1/13, 24. Hopefully there's no errors here. So I want 1/4 of row 1 added to row 2. 1/4 of that, that'd just be 3/13. All right, so now I'm gonna use my calculator for the next one because that's kind of a yuck. So negative 6/13 times 1/4, and then I'm adding it to 1/2. And that gives me 5/13. You don't need to do that in your head. 1/4 here, so I have 1/13 times 1/4. Oops, here we go. 1/13 times 1/4, and I'm going to subtract 1/4. And that gives me negative 3/13. And finally, I'm going to take 1/4 of this, that'd be 6, and add it to 24. All right. Now I'm going to take negative 1/6 of row 1 and add it to row 3. So negative 1/6 of this, that'd make that negative 2/13. Negative 1/6 of this would be positive 1/13. Negative 1/6 of 1/13 plus a 6th. Can I use my calculator for that one? That would be 2/13. And by the way, notice the consistency of the denominators. That's a good thing that I keep seeing the same denominator over and over again. Negative 1/6 of this plus this. So negative 1/6 would be negative 4 plus 9. That would make that a 5. Now, finally, the last row. Looks like I can just add row 1 to row 4. So 0, 0, 0, 12/13. Negative 6/13 plus 1, that'd be 7/13. 1/13 plus 0 is 1/13. And finally, 24 plus 75 is 99. Now, we are completely finished, but here's why we're completely finished. We have no negatives on the bottom row. That's it. Now we can read our solution, okay? Our solution is going to come directly from this. X1, X2, X3 are unit columns. And notice that S1, S2, and S3, the slack variables, all three of those are going to equal 0 because none of them are unit columns. They all got used up. So let's see if this solution, we're going to state our solution now. Let's see if it actually works. So I'm going to, let's see. Let me erase this portion here so I can fit in the solution. So we read our solution this way. We'd say x1 is what? x1 is 30. x2 is 24. x3 is 5. And finally, my profit is 99. Now you can represent your answer this way because x1, x2, x3 probably represent some form of resource. Use this many hours or this much money. This isn't a point in space necessarily. It is also completely correct to write it as an ordered triple. Say profit is 99 at 30, 24, 5. That's also totally acceptable. Now I think that's the right answer. Let's now go back and check. Let's use these numbers first. So 2 times 30, that's 60, plus 24, that's 84, plus 3 times 5, that's 99. Okay. Now going back to my inequalities, 30 plus 24 plus 5, that is equal to 59. There is nothing left. 2 times 30, 60, plus 3 times 5, that would be 75. Boom. And finally, x2, which is 24, plus 6 times 5, 30, is equal to 54. So here are 3 sets of inequalities. I ended up using up everything. There's no unused portion. But if I had tried to solve this as solving a system of inequalities and trying to do it like we did last day, I would literally need to build a model bounded by multiple planes, then enclosing a geometric shape, some sort of polyhedron, and then try to figure out where the vertices were, which, by the way, would be very, very difficult in general. That would be nightmarish. This process, though, is so clean. Is it messy? Sure. Is it tedious? Yeah. But all I need is a calculator to do the little simple fractional stuff, because that stuff is kind of nasty. Now, this is the simplex method. The simplex method is when you are maximizing something subject to a system of inequalities that are all less than or equals. So the problem with greater than or equal is greater than or equals unbounded. It can go forever and ever and ever. So this is the simplex method. So, but now we're going to look at a problem. What if our constraints are reversed? What if these are greater than or equals? So I'm going to take a really simple 2-dimensional problem. Again, I'm going to go back to what we did way back in pre-calculus or algebra class and look at that problem. This eraser is dying on me here. All right, so let's suppose, hold on a second. There you go. All right, so here's what I'd like to do. We've been maximizing, and I called it profit because it makes sense, right? Farmer Jones has his peas and corn in his acres, and you're trying to maximize the profit. Okay, you don't try to maximize costs. You try to minimize costs. Oh, so it's the other way if I'm thinking about, right? Maximizing profit, I want everything to add up to as much as it can. Now I want to minimize the cost, which let's say is equal to 6x1 plus 8x2. x1 and x2 are my variables. So maybe again, it's acres of peas and corn, but I want to minimize how much money I'm spending, okay? Subject to the following inequalities. Subject to 2x1 plus x2 is greater than or equal to 25. Make sure I can read my own writing here. Hold on. 3x1 plus 2x2 is greater than or equal to 42. x1 plus 4x2 is greater than or equal to 24. Okay, and of course, like before, x1 and x2 are non-negative. So this creates a picture. I'm going to go ahead and draw it. Okay, so if I draw the lines, not the inequalities, but if I draw the lines, okay, the first line would be something like this. And that point would be 0, 25. The greater than or equal means I'm on this side. The second line, this guy here, let's say about that point is 8, 9, where they intersect. The third line, which has a very shallow slope, is going to look more like this. Now, I am not interested in this point of intersection. I am interested in this point of intersection, which would be 12, 3. And then finally, I am actually interested in that point of intersection, which would be 24, 0. Now, I've done the algebra ahead of time for you, so you don't have to worry. What you would do is make these equal. Make this equal to 25, make this equal to 42, and then figure out where the lines actually intersect. And then do the same thing here and here. You notice I'm not concerned with this point of intersection because these are all greater than or equals. That means, remember, you test an inequality by just simply testing a point. 0, 0 does not satisfy any of these, so it means I'm on the opposite side. So essentially, this is what we're looking at. So we're in the first quadrant, we're bounded by the axes, and we're in here. So in other words, this is open-ended. This goes forever. This is not a closed region like what we did last day. But I also want to minimize, which means, again, I want probably one of these 4 vertices. Because like I showed last day, I'm bounded by linear functions, okay? And using calculus, right? Extrema can only occur at critical values or endpoints. I have no critical values on lines, I only have endpoints. So there's only 4 places that an extrema could occur. Now, depending on the size of the coefficients, I could make it so, for example, if this number were really, really, really small compared to this number, then I would probably want this value. Or I'm sorry, let me say that. If this number were small compared to this number, I'd probably want this value. If this number were small relative to this number, I'd probably want this point, and then so on. So let's look and see what we have. We have 4 points. So I'll put them down. 0, 25, 8, 9. The origin is not a possibility this time. Okay, given what I have up there, let's calculate each of these things here. So 0, 25, so 0 and then 8 times 25, that'd be 200. This is probably dollars, by the way. 8 and 9, so 48 plus 72, that'd be 120. 72 plus 24, that would be 96. And 6 times 24, that'd be 144. So right now, given this information, and I just simply drew a picture, this is a pre-calc or earlier problem. So if I had asked you to minimize this subject to all of this, you would have drawn this picture in the algebra class. You would have figured out the intersections. You would have calculated the cost of each one. And the winner clearly is here. I will minimize the cost if x1 is 12 and x2 is 3. Okay, great. Problem is, what if I have more variables? Then I can't do it as a picture, okay, just like before. So I'm going to show you how to do basically the simplex method on this problem. Then obviously, if I have more variables, we use the same method. Last day, I did the simplex method on a 2-variable problem to illustrate we got the same solution as we did graphically. Now I'm going to do the same thing for a 2-variable problem to illustrate we're going to get the same solution. So then you can beef it up if there are more variables, okay? Problem is, these inequalities, they're going in the wrong direction. So Let me erase this because I no longer need my picture. Remember the answer, 12.3, and we got a cost of 96. That's very important, because hopefully that's the answer we're going to get. So what we start by doing is we make what's called the simplex tableau. It's basically like a matrix. It's not really a matrix. It's a rectangular form where I'm putting all the numbers in, and it's going to look like this. We didn't bother doing this on the simplex. We created our slack variables and then just basically went right to the matrix. Here's what I've got. I've got 2, 1, 25. I've got 3, 2, 42. I've got 1, 4, 24, and I've got 6, 8, and at the moment my cost is 0. Okay. I want to take the transpose of this. Okay, this is what we're doing today. I want to take the transpose. So when I take the transpose, 2, 1, 25, 3, 2, 42, 1, 4, sorry, whoops, sorry, 1, 4, 24, sure I did it right. And then the last one would be 6, 8, 0. Real quick check, so 2, 3, 1, 6, 1, 2, 4, 8, 25, 40. Okay. What we're going to do is create a new system of inequalities with new variables. Everything's going to be completely new. We are essentially doing a form of a transformation. Think polar coordinates for a moment. This isn't polar coordinates, but in polar coordinates, you'd say, I'm going from XY world to polar coordinates because I can do that problem easier. For those who've had Calc 3, right, I might use cylindrical coordinates or spherical coordinates to do a translation. In Calc 1, I'm doing a U substitution. That is a form of a transformation. I'm doing a problem with different variables that's going to get me to the same place. In this case, this is a form of transformation. We're leaving X1, Y1, or excuse me, X1, X2 world. We're going to go to a different planet. We're going to get the right answer, but we're going to do it by making a substitution in a sense. So I want to create a new system of inequalities based on this, and I'll use 2 new variables. We were using X1 and X2. Now we'll use Y1 and Y2 and so on. So the first line, I read it like this. Hold on. It's going to be a little bit. Yeah, I'll do it. I'll do it here. I'm going to erase those in a moment. So now I have, it's fitting everything on. Here's the tricky part. 2Y1 plus 3y2 plus y3 is less than or equal to 6. That's how I'm going to read this. Then I have y1 plus 2y2 plus 4y3 is less than or equal to 8. And then the last thing is, I'm going to write it this way. I want to maximize 25y1 plus 42y2 plus 24y3. And that's going to be my profit. So cost, now that's going to be the profit. Okay. This is called the dual problem. I have one problem on one side, I have another problem on the other side. I can't solve the original problem because the inequalities are going in the wrong direction. I cannot introduce negative slack variables. That doesn't work. But now I have a situation, and by the way, y1, y2, and y3 are still non-negative. Now I'm going to solve this problem right here, right in front of me. Forget that one. I'm going to solve this problem using the simplex method as we had just done before. So now that I've created a new problem, the next step is to now create my slack variables so that I have a system of equations. There is no matrix. There is no such thing as a matrix for inequalities. That does not exist. There is no such operation, impossible. I'm creating a problem. This looks like what we've already done. So I'm going to say 2y1 plus 3y2 plus y3 plus slack variable 1 equals 6. y1 plus 2y2 plus 4y3 plus slack variable 2 equals 8. Negative 25y1, negative 42y2, negative 24y3 plus p equals 0. That is exactly the problem that we were just doing earlier. We're going to solve this problem using the simplex method. Then I'm going to show you where you read your solution. Now, notice something interesting. My original system of inequalities, I have two variables. I have three sets of inequalities. My new dual problem, I have three variables and only two sets of inequalities. Those will always flip-flop. That's interesting. It's always going to do a little flip. So I'm going to use this space up here to start the problem, because otherwise I'll never fit it on here. And I'll use black. Okay, so got 2, 3, 1, 1, 0, 6. I've got 1, 2, 4, 0, 1, 8. I've got negative 25, negative 42, negative 24, 0, 0, 0. Hopefully everyone can see that easily. Okay. Perfect. All right, now let's select our pivot. All right, anybody, what column am I going to choose? First, second, or third? Hopefully you've been paying attention.
Second.
First, second, third. Second, because
It's the most negative.
yeah, it's the biggest negative. All right, so now I'm picking that column. I only have two choices. Am I going to choose 3 or 2? Do I pick 3 or do I pick 2 as my pivot?
2.
2.
You sure? How do I choose my pivot? The smallest positive ratio. 6/3 is smaller than 8/2. Okay, you gotta get that one right. If I choose the wrong pivot, I will not get the correct answer. Yeah, you gotta pick that one. Again, 6/3, 8/2. Which one's smaller? 6/3. So I choose the column that has the largest negative, but then I choose my pivot by the smallest positive ratio. That's why if one of these had a negative sign in it, I probably can't use it. All righty. So I'm going to go 1/3 of row 1. So 2/3, 1, 1/3, 1/3, 0, 2. And then everything else just goes along for the ride. Okay, and then yeah, I'm a big fan of doing this so I don't lose track, because there are other ones on there and I don't want to all of a sudden forget which one I'm working with. That would be bad. Okay. So I think I can get this in here. -2 row 1s plus row 2. Okay. -2 row 1s. Okay, let's see, is that right? So where are we? -2 row 1s. So what would -2 row 1 plus row 2 look like? Well, -4/3 plus 1. Actually, let me rewrite row 1 first. Okay, so -2 of these, that make that a -1/3. -2 of these. -2 of these, that would make that 10/3. -2 of these, that'd be -2/3, 1/4. Now, 42 row 1s plus row 3. 42 times 2/3 is 28. 28 plus -25 would be +3. 42 of these, that'd be 0. 42 times 1/3 would be 14. 14 plus -24 would be -10. 42 times 1/3, that'd be 14. Then 0. 42 of these, that would make that 84. Okay. We're not done because of the -10. So I have to do this probably only one more time. All right. So when I'm looking at this, 2/3, 4/10, which is smaller? 2/3, 4/10. Anybody? So I've got 2/3, that's 6, 4/10, that's 6/5. Pretty sure I'm going to go there. So I'm going to choose the 10/3. So hopefully you guys can all see that sort of. So this is -1/3, 0, 10/3, -2/3, 1, 4. My pivot is going to be the 10/3. So now I'm going to multiply that row by 3/10 in order to get a 1. So 2/3, 1, 1/3, 1/3, 0, 2. I'm going to multiply this row by 3/10. So that's going to be -1/10, 0, 1, -1/5, 3/10. I'm multiplying the row by 3/10. So that's 12/10, okay, or 6/5. And then I don't do anything to this row here. All right, this is probably the last step of the problem. Okay, so I need to take 10 row 2s and add it to row 3 eventually. So let's first go the other way. I think I can fit right here. All right, so let me write that row. 10, 0, 1, -1/5, 3/10, 6/5. All right, I want to go -1/3 row 2, and I want to add it to row 1. So let me get my calculator. -1/3 of these and that gives me 7/10, 0, excuse me, 1, 0. -1/3, that would be 1/15 plus 1/3. And that would be 2/5. Let's see, so -1/3, that's -1/3, so that'd be -1/10. -1/3, so that'd be -2/5 plus 2 would be 8/5. Okay, so hopefully we are correct at that point. Now 10 row 2s plus row 3. So 10 times -1/10 would be -1, added to 3 would be 2, 0, 0. 10 times -1/5 would be -2. When I add it to 14, I get 12. 10 times 3/10 would be 3, added to 0. And 10 times 6/5 would be 12, added to 84. All right. We are finished because my bottom row has no negatives. Now, here's the weird part. I'm not going to read my answer the same way. You see, if I did, I've got y1 is 0, y2 is 8/5, y3 is 6/5, and my profit is 96. Problem is, I'm not trying to find y1, y2, and y3. I'm trying to find x1 and x2. Oh, how am I supposed to do that? Well, here's the thing. This is the dual problem I said. The dual problem, my original problem had 3 variables, 3 inequalities, 2 variables. The original problem, again, 3 inequalities, 2 variables. My dual problem had 3 variables, 2 inequalities. But I want you to know something very important. I introduced exactly 2 slack variables. The slack variables, as it turns out, is where the answer is going to come from. It's crazy. It's kind of cool. We took the original problem, had to alter it to make a system of inequalities where they're less than or equals. When I did so, I introduced 2 slack variables. That matches the number of variables up here. I did the problem all the way to the end, but I'm not reading the answer for y1, y2, y3, because y1, y2, y3 don't actually exist in X world. Notice something. Does anybody notice anything? Wasn't that X1? Wasn't that X2? And wasn't that our cost when we drew the picture? Does everybody see that? Remember, we knew what the answer was going to be. At 12,3, we had a cost of 96. That's what we did when we drew the picture. So I wanted to do this whole problem so you could see where the answer is going to show up. When you do the dual problem, you stop at the exact same place you would stop with the regular simplex problem. But you read your answer from a different place because there are no y1, y2, y3 variables. Those variables aren't actually, in this world. So when I finish the dual problem, the answer will always come from the bottom of where the slack variables were, because the number of slack variables in the dual problem always matches the number of variables in the original problem, always. Okay, so the answer is I'm going to minimize my cost, get 96 when x1 is 12 and x2 is 3. Now, again, we did it geometrically. We did it by drawing a picture and doing it that way. And that only worked because there were two variables. So that's not going to work in general. Also, it becomes really, really tedious and difficult to manage if I've got many, many, many different constraints. So this is an interesting problem. So this is the simplex method. This is what you are responsible for from chapter 9, these two things. Now, this section here in the Larson section 9.4, the simplex method is the dominant theme. This is an alternate version, again, called the dual problem, because I can't do the simplex method on the original question yet. I had to alter it and make a new problem. That's what the dual problem is. It's my alternate version. It's my transformation. I solve that problem using the simplex method, and then I go back and read the solution. Okay, so that's where we are. That's what I wanted to cover. Stop recording.